But with the advent of quantum materials, new things need to be deciphered to understand what's really going on. So for example, I work mainly in topological insulators and topological superconductors. And really that, you can have the crystalline structure right, you know that it conducts electricity, but what you really want to know, and the sort of last characterization step in quantum materials should be, or in topological materials should be, is it topological? Or if it's a superconductor, a topological superconductor, does it have Majorana fermions? Are there things that we can characterize about the material that tell us it is in fact a quantum material? And I'm not even going to try to define what is quantum material today, but the main examples I'll be giving focus on my own research, which is mainly topological insulators and topological superconductors. So just to contrast these sort of newer versions of topological materials, the one I'll be talking about today is tin telluride, which is a topological crystalline material. The first quantum material I worked in was graphene. I came into the field before it was fully known what graphene actually did. When I was a first-year graduate student, Paul McEwen came by and showed this band structure and started making inferences about neutrinos and some high energy physics to try to excite the crowd, but he backed off a little bit about it, saying, well, I don't want to take this analogy too far. But then using simple electrical measurements, we are able to back out the fact that graphene does in fact have this band structure, and the interesting physics associated with this band structure could be measured in a simple transport measurement. So if you take the graphene sheet, you make a device out of it, you put it in a high magnetic field, there's a signature in the quantum Hall effect that tells you that all of the interesting physics that Paul McEwen wanted to get out of this band structure actually exists. And so it was a nice transition from what I would call non-quantum materials to quantum materials, again with the caveat that I don't think there's a very strong divide between those two categories. But there was a nice transition into this quantum material and graphene in terms of its characterization, because we could apply all of the techniques that we knew how to do, and we can get a binary answer about whether this was in fact as interesting as Paul McEwen had hoped it would be. Now moving into more complicated materials, it turns out that this binary test for some of the more interesting properties doesn't exist. And there are a lot of questions about, well, I'm actually happy to talk to mostly graduate students and a few postdocs. I see this characterization problem as a key piece of the puzzle that needs to be rectified moving forward in quantum mechanics or quantum materials. And so as you start to synthesize these materials and characterize them using the traditional methods, I encourage you guys to think forward about what types of measurements would need to be made to say, yes, this is topological, or yes, this is a, like for example, tomorrow we have a conference. Yes, this is a topological condo insulator. About half of my group's focus since I've been here at Maryland is focusing on developing these techniques. These techniques are, at least for me, rather complicated. One that has really stood out so far is an old device called the Josephson Junction. And using the simple combination of a Josephson junction and an RF generator, we've been able to elucidate some of the more interesting properties of these quantum materials. I won't go through, this is not going to be an advertisement, although technically it's something I should do at one of these things. It's not going to be an advertisement for the work that I've done so far. Using this combination of just a Josephson junction and an RF generator. I put this slide up as a highlight. I'll be around today and tomorrow if anybody wants to talk further about some of the work we've done. I'm happy to chat with you. One of the things I'm most excited about is this isoliton. And so niobium diselenide, there are multiple bands which contribute to transport. Seems that I've lost your.
The pointer?
No, I have it, but it's gone dead. Do you have another one? Something that actually JP knows about a little bit is that in niobium diselenide, there's two bands. Niobium diselenide is a superconductor, and the question really is, how does a superconductor relate to each other in these two bands? And if there's weak coupling between these two bands of superconductivity, some very interesting phenomena can happen with Josephson junction-like physics between these two bands. And we think for the first time we've actually seen this interband isoliton, as it's called, effect in Josephson junctions created from niobium diselenide. This is a rather long topic, so I decided not to do it today. What I'll be focusing on more is Josephson junctions that we've fabricated from a topological crystalline material, tin telluride and its cousins, lead-doped tin telluride. But before we get into the measurements, I just want to tell you a little bit about the properties of Josephson junctions. And then we'll use some of these properties to probe quantum materials. I don't want to give the impression that I think Josephson junctions will totally determine all the properties of the quantum material. However, I do see, I mean, there are flaws in understanding some of the things you extract from Josephson junctions of quantum materials. But it does go a little bit of the way to show how, by changing the way you do measurements, you can extract much more information about these key characterization questions that we want to get for quantum materials. And so Josephson junction is basically two superconductors that are separated by some material that's not superconducting. Traditionally, this falls along the lines of an insulator like aluminum oxide, which separates two superconductors on the right and the left. Each one of these superconductors has a wave function or order parameter associated with it. And when, since the Cooper pairs are not allowed in this insulating barrier, that wave function will decay exponentially. If I bring these two superconductors close enough together such that they can start to talk to each other, this overlap allows a supercurrent or a resistanceless flow of Cooper pairs between the two leads on the left and the right. The simplest way to back out the properties of this material is to basically use this two-state approach where you have a wave function on the right and left, and there's some coupling, this transmission or transfer Hamiltonian, some coupling that allows you to, say, hop a Cooper pair from the left to the right or the right to the left. So just basically by writing the order parameter as some square root of the density of Cooper pairs in some phase, and separating out the real and imaginary parts of the time-dependent Schrodinger equation, and allowing for, say, a voltage to exist, a voltage difference to exist between the left and right lead. If you solve these equations, you come to two of the most fundamental equations that govern the behavior of Josephson junctions. The first one dictates the supercurrent that flows through the junction, and you can see that supercurrent depends on the phase difference between the left and the right lead, and in this simplest approximation, its dependence on this phase difference is sinusoidal. It also has an amplitude, which depends both on the density of Cooper pairs and this coupling constant that basically is set by the overlap of the two wave functions within that junction. And so the amplitude says something about the superconductivity in each lead and the coupling between those two things. There's a sinusoidal dependence on the phase difference. And the other equation that pops out is this equation that determines the time rate of change of the phase difference when you apply a voltage between these two conductors, or these two superconductors. So if I apply a voltage between these two superconductors, the phase difference between them will evolve linearly in time. These are the DC and AC Josephson relations that you might be used to. So for 50 years or so now, people have been making Josephson junctions using an oxide barrier as the material that separates two coherent phases of these superconductors. This oxide interface form of junction forms the basis of what people use for quantum computation now, using these Josephson junctions. But a little bit about what Javad talked about last time. Starting in the 90s, people started to couple the two superconductors with another material that wasn't superconducting but was allowed to conduct. So say a piece of metal or a semiconductor. And there the fundamental processes which govern the transfer of Cooper pairs is quite different. So this is a cross-section of what we call an S-N-S junction, where you have two superconductors that are coupled by this conducting metallic layer. Inside this metallic layer, there are no Cooper pair-like excitations. There's only electron and hole-like excitations. So if a Cooper pair wants to be transferred from, say, the left lead to the right lead, it needs to go through this normal region, and it can only go through as an electron or a hole. So a Cooper pair basically eats up one of these holes that exists in the Fermi sea in the normal metal and spits out an electron. Before that electron can enter the second superconductor, it needs to pick up another electron to form the Cooper pair. And when it does, it creates a hole that is then retro-reflected back to the other junction. And this process kind of happens in a very Fabry-Perot-like interference pattern. Since this electron and hole state is bound to this small region in between the two superconductors, we call this a Andreev bound state. It is these Andreev bound states which are fundamental in the transfer of Cooper pairs from right to left. And what we're going to end up doing, and I'll show a little bit about more about this later, is that when we use interesting materials, we can actually affect the Andreev bound state pattern that forms. And by detecting that change in the Andreev bound state pattern that forms, we can say something about the interesting material that lies between this. So this is how we take Josephson junctions and sort of turn it on their head. Rather than just looking at something that carries a supercurrent, we actually use it to investigate the band structure properties of the material that exists between these two superconductors. So like I said, we now have a normal conducting region. This normal conducting region mediates the transfer of Cooper pairs between, say, the left and right lead. One thing that this does do is it modifies this current phase relationship. You might remember, well, I had J on the other slide, but it was just J equals sine phi. But when you start to make these interfaces clean and the material much better, like Javad does, there's a whole host of higher harmonic terms that come and become very important in determining the relationship between the current and phase. And again, just to stress this point again, this relationship between the current and phase has everything to do with the Andreev bound states that exist in this junction. So I just wanted to write down these two fundamental equations again, the DC and AC Josephson effect. The AC Josephson effect, at least in its equation form, look very similar. The DC one is similar, but there are higher harmonics in this relationship between current and the phase difference. So a lot of what I'll be talking about is the AC Josephson effect. To measure the AC Josephson effect, you need to apply an RF field to your device. Typical RF fields that we applied are RF electric fields to the device. Typical frequencies which we apply are 1 to 10 gigahertz. I'll show how the frequency changes the AC Josephson effect again in the next slide. But I want to first just understand what happens in the dynamics of a Josephson junction when you apply an RF field. So this is for a conventional sinusoidal I equals IC sine phi current phase relationship. To understand the free energy of that junction, you basically take the integral of that current phase relationship, so you'll still have a periodic potential. So this is now the Josephson energy in the device versus the phase difference between the two leads. Typically under no applied current or RF radiation, you can think of the dynamics of this junction as this tilted washboard potential model. So there's some bead that exists in this periodic potential, and the dynamics of the Josephson junction can be inferred by understanding the dynamics of this bead on this periodic potential. So the AC Josephson effect, let's say I apply no DC current, no RF current, this bead is just going to sit at the bottom of the potential well. Now, if I start pumping this with an RF field, you can think of taking this tilted washboard potential and moving it up and down. This is the equivalent of applying a RF radiation. And under the right conditions, if I pump this junction just right, for every time I pump, I can actually get this bead to hop one minimum at a time. And we know that the d phi dt gives a voltage. So if I'm controlling the hopping between minimums, I'm controlling the time evolution of the phase in a very specific way. For each time I pump, I get one hop in the minimum. That controlled time evolution, d phi dt, remember the AC equation, d phi dt is equal to something voltage. If I have a controlled evolution d phi dt, that's going to give me a voltage across my junction. And how that Josephson, that voltage manifests itself is regular steps in the IV curve that you measure. So this is the differential of those IV curves. You can see these regular minimum. The minimum of the currents are in black. I'll talk a little bit about this in a little more detail later. You'll see one-dimensional cuts of this. But this pumping, which moves for every pump, the minimum at which this ball lives in is determined by the frequency. And so the voltage you get is actually related to how fast you pump. If I pump faster, my ball is going to hop faster along this well. That's going to give me a higher value of DC voltage. And so if you look at the steps in the DC voltage, they're frequency dependent. And for every half gigahertz you apply, you get a 1 microvolt step. So if I were to say to jiggle this up and down with 3 gigahertz, I would expect voltage steps at, say, 6 microvolts. And one of the interesting things about this Shapiro step measurement is it depends very sensitively on the details of this potential. So this was a potential for a current phase relationship that was sinusoidal. If I start to modify that, the types of patterns I start to get out of these junctions changes. And I can use these patterns to back out information about what my potential looks like, therefore say something about what the current phase relationship looks like. So this Shapiro step, which is nice because you can think about this classical effect of just pumping this ball within this tilted washboard potential, can tell you something about the current phase relationship, which can then tell you something about the Andreev bound state spectrum, which also can tell you something about the material. So to start, I'll just talk about how we fabricate these junctions. One of the practicals was on e-beam lithography. What happens in e-beam lithography is electrons are collected off of some filament and accelerated to high voltages. I'll talk in a little bit about what those high voltages actually do and why they're important. This beam of electrons is diffracted through a combination of electrical and magnetic lenses, and then are focused down onto the sample. The sample has something on top of it. The typical something that you put on top of it is something called polymethyl methacrylate, which is a polymer chain of these, whatever that is, I have no idea, some chemistry thing. But the important thing is that when chains of these molecules see the e-beam, they start to break apart. So let's say this is my film, I've shown the e-beam right here. Where the blue is darker, these chains have been sliced apart into their individual constituents. And then those sliced apart polymers are now soluble in a certain solution, whereas the ones you didn't slice apart are not soluble. So if you put it in a solvent, what you get is a pattern that looks like this. So you can transfer a pattern that you generate on this electron beam lithography system onto your sample, and then you could say deposit leads, which again I'll talk about in a little bit. Now let's see, almost 3 years ago now, we got a new e-beam lithography system. That's the one you saw in the practicals for those of you who went. We needed to upgrade the system to a higher accelerating voltage, and you might say, well, why do you need higher accelerating voltages? Well, what you need to look at is what happens when the electron beam comes down and hits this polymer. For low accelerating voltages, like say 10 or 30 keV, that electron comes in. Most of them go all the way through, but a few scatter. So let's say I only wanted to dose right at this point right here. I would dose along that point, but then there's a whole lot of straggle of all these electrons, and all those electrons will then dose the polymer, break apart their chains, and become soluble. So let's say I tried to make a 10 nanometer line. What I would see is like a 50 or 100 nanometer line. And this diffraction effect at the surface, this straggle effect, is strongly dependent on the incident energy of your electrons. So if you increase the voltage of the electrons and increase their velocity, what you do is decrease the straggle, and there you're only actually dosing right in the polymer where you want. And so this is just kind of a look at the actual dose profile that you get for different electron incident energies. I believe this is for 10 keV, this is for 100 keV, and you can see you get a much narrow distribution of electrons. So if I were to take each of these samples and develop them, this one would be developed over a very wide region, and this would be developed over a very narrow region. And you can see the effects of this straggle as you turn up the incident electron energy. You can see how these ones at 30 keV are really bowed at the bottom, and this is all due to this straggle effect. For those of you who have e-beam systems that run down 30 keV at your different schools, one trick to reduce this scattering or reduce this straggle effect and this bowing when you do development. So most of the polymer that gets irradiated in this region is partially, it's not completely chopped up into individual units, but they'll be partially chopped up, and the combination of the solvent and some amount of heat, say room temperature, is what allows this wider region to be developed. So if you actually use 30 keV, one way to kind of increase your resolution is to develop in a cold. So take your developer and put it in an ice bath or something. That will remove some of these wide regions that have to do with these thermally assisted dissolution of the polymer. So just a quick trick in case you don't have one of these fancy $2 million machines that goes to 100 keV. So for our junctions, how do we actually make them? We spin the polymer. You guys probably saw a little of this at the practical on the last few days. We spin polymer on top of a topological crystalline insulator, showed here as a lented telluride. We then develop, we expose these regions here and here and develop away the polymer. And then we take this, we put this in a sputter deposition chamber, and we sputter a little bit of tie, about 3 nanometers of tie as a sticking layer. Well, actually, tie serves two purposes. It allows the aluminum to stick, but tie is also a great getter, so any sort of oxygen impurities that might affect your aluminum get eaten up by titanium, and titanium remains conducting. We can then do what's called a liftoff layer, where we put this in a solvent like acetone. We have a little bit fancier solvent than that, but that's not important. And in that solvent, this PMMA will dissolve, and it will lift off any metal that's above it. And what you're left with is 2 pieces of aluminum that are separated by some small region that you defined using your e-beam lithography. So this is what our junctions actually look like. We start with a large wafer where the lead tin telluride or the tin telluride is everywhere. We then etch away most of the lead telluride. The reason being is that it's conducting, so we want all the current to flow through the junction, and we don't want any shunt conduction that bypasses the junction. You can zoom in on this region, and you can't look anymore with optical microscopy. You need a scanning electron microscope to actually see the junction. The junction is here. This is a aluminum lead, and then you can't see it in black, but there's a small region of lead tin telluride in between those that facilitates the transfer of Cooper pairs from, say, the bottom to the top. And so typically, the types of resolutions we can get for this dimension, the spacing between two leads is about 50 nanometers. We can push that down to about 30 nanometers now, doing some fancy lithographic tricks that I can tell you about if you're interested. The deposition is all done in this dual sputter deposition, E-beam deposition machine. We try to keep our superconductors separated from every other material that we use for electrical contacts to enhance the quality of the superconductor. It's not such a big thing for aluminum, but more important for things like niobium, niobium tinitride, etc. One other thing that we do prior to deposition of the titanium and aluminum contacts is we actually etch out the contacts before. So you'll do this deposition step, you'll remove the PMMA where you don't want, but it turns out right here there's still a lot of crud kind of left behind after you do this development. So what you want to do before you put this on is we actually argon etch out to try to remove any hydrocarbon or oxygen-based crud that might be sitting on the surface of the material. And we do that all, we do that just prior to the deposition of the Ti aluminum leads. For these particular samples, we cleaned out the leads using this argon deposition. We made the junction length as small as possible so that the two superconductors were as close as they possibly could. And we found that we could only get a supercurrent when we heated the sample during deposition. And so you'll see a lot of curves that looks like this. This is a plot of the differential voltage, the lock-in voltage as a function of the DC current through the junction. If it is actually a Josephson junction, you would expect there to be no voltage developed as you start to apply a DC current. This is the voltageless superconducting state. And this only persists up to some value of current. At some value of current called the critical current, there's a jump into the normal state. And so you'll see a lot of plots that are dVdI versus this IDC. And these peaks in dVdI indicate the position at which the device goes normal, which we call the critical current. So just to bounce off of what Javad said in the last time, this interface is a rather complicated, dirty thing. And we've been doing this now for almost 2 years, and we have really no idea why heating these contacts enhances the superconductivity that's induced in the region in between the two superconductors. So just real quick, I talked a little about the origins of these effects, but I just want to say explicitly what the measurable experimental data is for these junctions, the two most important things being the magnetic diffraction pattern and the Shapiro steps associated with moving that tilted washboard potential up and down. One question would be, what is this critical current, or the point where the device goes from superconducting to normal? How does it depend on magnetic field? And so you can think about, so this is my superconductor, this is the other superconductor, this is a junction in between. Want to know what happens when I put a magnetic field into the board. And so let's say I put one flux magnetic field in this region into the board. Then when I look at the phase evolution along this junction, I should get a 2 pi phase evolution from the Aronoff-Bohm effect along the width of this junction. And so since, remember, the critical current or the supercurrent looks like IC sine phi. And so if I allow phi to evolve by 2 pi, I should basically go through my whole sinusoidal curve of the current phase relationship as I go along the width of this junction. And since sine has an average of 0 over one period. If I put one flux such that the phase has to evolve by 2 pi across this junction, I basically can trace out my current phase relationship by putting one flux through the device. And since the average is 0, when one flux is going through the device, you have half a supercurrent going this way, the other half going this way, and it gives you a 0 overall in the supercurrent. So if you look at the pattern traced out for a junction that is uniform and it has a sinusoidal critical or current phase relationship, you see this, what's called a Fraunhofer pattern. This is the same pattern you get in a single slit diffraction. It's basically, you might remember, is the Fourier transform of some box function representing the supercurrent through the device. So this is one thing we always look for when making our junctions, because one of the failure modes that happens is you might have a junction but then a small little superconductor that didn't lift off and is kind of shorting your junction out. It'll have a small supercurrent, so it looks like it's going through the junction, but it's really not the Josephson junction we want. But if we can measure some Fraunhofer-like pattern, we know that there's a roughly uniform distribution of supercurrent, no shorts in the device. And we're actually going to use this pattern too to investigate some of the properties of the material. The other thing is the experimental effects of the Shapiro steps, or driving these junctions with RF radiation. I said that if you can control the phase evolution, you should get steps in the DC voltage, because there's an irregular progression of phase with respect to time. And so if I look at the effect of just the DC, to say voltage versus current that I apply, I see steps in the voltage that I measure. And these steps are determined by the frequency which you apply to the junction, i.e. how fast you move that thing up and down. So if I move it up and down faster, I would expect these steps to get higher. HF over 2E would be bigger. One of the first things that was proposed to use this measurement for was to look for Majorana fermions. Majorana fermions don't have a sinusoidal current phase relationship. They have a relationship that goes like sine phi over 2. So actually, all of your junction or your Shapiro steps height should be doubled from that over 2 term there in the current phase relationship. This measurement has a lot of caveats that are details about the Josephson junctions. I'm happy to tell you about those caveats if you're interested. What time did I start, JP? Like 11:20?
You got 20 minutes.
All right, go. So I just want to review a little bit of work we've done with topological crystalline insulators that we fabricated into Josephson junctions. Topological crystalline insulators is a topological system protected by the crystalline symmetry, specifically the mirror symmetry of the crystalline lattice. This has, at least in terms of eigenvalues, a very similar effect that time reversal symmetry does. So for those of you who are more comfortable with things like bismuth selenide, the mathematics is very similar to bismuth cyanide. The only little footnote that I'll add to the differences between the two, well, actually, I won't. That is not relevant for this particular talk. And so, I'd like mostly to contrast the striking differences that you get in transport when you look at a Josephson junction made from this material versus just a regular old, I'm going to slap some contacts on and measure its properties as a function of magnetic field. When I say slap some contacts on, I mean normal contacts like gold or palladium, whatever you're used to using to make contacts. This is a map of a device we made with gold contacts with tin telluride nanowires. These nanowires were grown by Judy Cha, who you guys heard from on Tuesday. And this is the applied magnetic field perpendicular to the junction and the DC current that you apply through the junction. You can see there's basically nothing. This is one of the problems that, at least from my perspective, we've always had with topological materials. Yes, they may have interesting surface properties, but there's a whole lot else going on that involves transport. And typically, that whole all else stuff going on, bulk conduction, et cetera, doping at the surface, these are the things that dominate transport. So when you do transport measurements, you don't see anything interesting because it's all shunted out by this large bulk contribution or some non-trivial surface state that exists on the surface. Now what we want to do is we want to be able to tease out some of the interesting features that may or may not be on the surface using a Josephson junction. And I'd like to illustrate in these next few slides how we actually do that. So just to remind you, there are these there's two superconductors that are coupled by this region that has normal carriers. These normal carriers interface with the two superconductors to form these bound states of electron-hole pairs. And these bound states are the ones that determine the current phase relationship, and I'll show you how that's done now. So plotted on the first graph is the energy of these Andreev bound states as I tune the phase difference between these two superconductors on the left and right. And what I want to look at is the evolution of these energies of these Andreev bound states as a function of something that was called tau, which is generically the transmission probability that you make it, say, from a Cooper pair being over here to a Cooper pair being over there. So it really has to do with both the transparency of the interfaces, but also the quality of the material. Are you ballistic or diffusive within that material? And if I look at the energy as a function of this transmission probability, I see that there's a crossing at 0 energy when the transmission is 1. The transmission is often not exactly 1, but very near 1. As soon as you move away from transmission equals 1, you start to get a small gap that opens up between the energy of these Andreev bound states at a phase difference of pi. Now from this energy of Andreev bound states, I can calculate the current phase relationship. And what we see is that as tau changes, hold on. Hello? Okay. Thanks. 1 second. So, one, I've always wanted to answer a call during a talk, so thank you for letting me do that. 2, I just need to make some quick changes to the fridge whilst giving the talk. So right now the helium-3 is getting filled up. And when that thing gets to, right now it's like 690, almost 700. When it gets to 1400, give me a call. All right, bye. So this is nice actually, because this is where we actually make our measurements of these Josephson junctions. This is a dilution refrigerator. And the reason I'm so concerned, other than that I want physics to keep going, there's $50,000 of helium-3 right here. And even if I had $50,000 just to spend for fun, it's still not easy to get. You have to go through a bunch of hoops to actually get it. So this is our dill fridge. It has base temperatures of around 20 millikelvin, although not right now because of the power outage. Okay. So you can see that the effect of changing the transmission probability of how Cooper pairs move through these junctions, in particular how the normal state electrons move in this region, is if the transmission probability is half, which is very common in devices that used to be fabricated, what you get for this current phase relationship is something that's very sinusoidal. But as you start to change the transmission probabilities by either making your junction cleaner or changing the properties of the normal material that lives in between these two superconductors, what you get is an increasing skewness of the current phase relationship. And how this skewness manifests itself is, well, you know, as you move from a sinusoidal wave to a triangular wave, if you do the Fourier expansion for that, as you move to the triangle wave, you get higher and higher harmonics that you need to generate to form that waveform. So if I look at the Fourier transform of these, you'll see that as I increase my transmission probability, the Fourier amplitudes of the higher harmonics increases. And when I do a Shapiro step measurement, if I only had the fundamental, I would see only steps at the integer values that you would expect. But when you start to add in these higher harmonics, you start to see steps at half of what you expect, a third of what you expect, and a quarter of what you expect. So if I do a measurement of the AC Josephson effect, and I see these subharmonic structures associated with a skewed current phase relationship, I can say something about what the Andrea bound state spectrum of my device actually is. And I'll use the next few slides to show how we actually tease out some of the interesting surface states, properties of topological crystalline insulators, but you can see how it might go. Two things happen when transmission probability goes up. The amplitude of your supercurrent goes up, and the skewness also goes up. So let's say I had a junction that had a huge bulk background with very diffusive, low transmission probability particles. There's a lot of those around, so in normal straight transport they're kind of dominant when I look at conduction, but they contribute very little to the supercurrent because you see as T goes down, this amplitude of the supercurrent goes down. In addition, it doesn't contribute anything to the skewness of my current phase relationship. So if I have things that are highly if I had things on the surface, even in the presence of a large bulk background, if I had things that were highly transmitting, I would get a stronger contribution to them to the supercurrent. And also, if I measured the AC Josephson effect, I would be able to pick out their skewness by seeing these subharmonic steps. So we did the AC Josephson effect for, this is lead-doped tin telluride, by all intents and purposes the same as tin telluride, at least for this magnitude of lead doping. This is the measured Shapiro steps where we see strong features at the integer plateaus. But in addition to these strong features at the integer plateaus, we start to see these half integer plateaus. One of the things I like a lot about lead-doped tin telluride topological crystal insulators compared to, say, bismuth selenide is we can actually turn off what is expected to be a topological state by tuning the doping of lead. And so we can look at just a lead telluride device and we can see what structure Shapiro steps it gives, and what we find is that we only see features at integer values of these steps, and for the frequency and bias ranges we played with, we never saw any subharmonic steps in the lead telluride. So it's our first indication that something interesting about the novel surface state is contributing to the Josephson current in these devices. So this is what I call the Shapiro step diagram, which is this is the bias current you put on. This is the power of the microwave frequencies you apply. And out of the board is dV di. Black is 0 dV di, so the superconducting regions. Now, if I apply sinusoidally varying voltage to the Josephson junction, remember d phi dt is equal to V with some constant. So if that V is sinusoidally varying, phi of t will also be sinusoidally varying. So if I put in sine of a sine, what you end up getting out is Bessel functions. So the power dependence of each one of these plateaus should be Bessel function-like, and that's exactly what you see. This is 0th order Bessel function, which has a maximum at 0 applied power, and then these are the first, second, and third order Bessel functions, which have a 0 at 0 applied power. Because these junctions can all be simulated using this very mechanical model of the resistively shunted junction model, we can actually simulate what's going on. So we basically simulate this equation, and what we do to change these simulations is we change the current phase relationship until we get something that gets a very good match. And what we found is that the current phase relationship, which matches most closely to the data, is something that's very highly skewed, which tells us there's something that's very highly transmitting in the junctions that was not apparent when we did our DC transport measurements with no Josephson junction. Now, where these highly transmitting modes comes from, I thought we had an answer for when we published this paper earlier this year, but recent work, which I'll tell you about next, has made me question whether that is actually the case. There are something that's very highly transmitting. We just might have guessed wrong where it came from. But to shed a little more light on this, we also made junctions from tin telluride nanowires. These are the ones from Judy's group, grown at Yale. And what you see, did I put? Yeah, so you remember, we're now going to look at the magnetic diffraction pattern, which should have this Fraunhofer-like shape. There's a maximum at B equals 0, and there's lobes. Now, there are many ways to distort this by, say, having the supercurrent be stronger in one region than another, which can modify this pattern. And we can simulate this for all sorts of kind of things that can go on in the junction. But one thing that is constant is that there's always a maximum in this critical current at B equals 0. Now, in our nanowires, what we see is that this Fraunhofer pattern is distorted, and there's actually a local minimum in the critical current around B equals 0. And if you, say, trace this out, this transition from black to purple, which is the transition from the superconducting region to the normal region, if you track out that as a function of temperature, you can see, so this is temperature starting at 60 going up to 300 or 400, I can't remember. As I increase that, what happens first is there's not a uniform drop of the shape as temperature increases, but these peaks, these anomalous lobes that have a higher critical current at a non-zero magnetic field, those are the first ones to die out. You see there's a much stronger dependence here than there is here. And then once you get into the high temperature regime, you start to recover a more normal Fraunhofer looking pattern. Now, where has this been measured before? In systems where there is a minimum at in the IC, a local minimum in the IC as a function of B. There's two systems that I know about where this has occurred. One is in corner junctions in D-wave superconductors. I didn't draw it down, but if I have a superconductor, which I could draw. So this is my D-wave superconductor. We know D-wave has a and I make a junction like this. So we know D-wave has this low B order parameter as Cooper pairs. So this is an aluminum, and my junction will be between this aluminum superconductor and the high temperature superconductor of this material. The Cooper pairs will tunnel preferentially along, say, the KY with a KY momentum. So they'll tunnel into primarily these positive lobes of the order parameter, whereas Cooper pairs over here would tunnel primarily into the negative lobes. So there's basically a phase, there's an out of phase component that comes from the fact that it's tunneling into two components of this wave, of this order parameter. And this gives you destructive interference at B equals 0. So if there were a perfect equal amounts of Cooper pairs coming from this part of the junction and this part of the junction, you would expect this to go all the way to 0 for this perfect destructive interference. Now, if there's some inhomogeneity such that this one is stronger than this one, then you get a pronounced minimum, but not all the way to 0 critical current. The other place, and the place that I've shown here, is in junctions that the weak link is made of a ferromagnetic material. And in these junctions, the exchange field provided by the ferromagnetic material has an effect on the Andreev bound states such that some of the Cooper pairs transfer straight through the junctions with a phase difference of 0, the others with a phase difference of pi. And this destructive interference gives you a minimum around B equals 0. So we have this in a material that is not expected to have anything interesting with, so this is just the resulting measurements. Don't want to say that other thing. Anyway, so these are ferromagnetic junctions. These are the effects on the Andreev bound states from the exchange field of the ferromagnetic material. How that actually works is not important, but the important thing is that it modifies the current phase relationship. So it takes something that was typically sine phi and produces something that was sine 2 phi. And so if I were thinking about where my Shapiro steps are going to be, if I go from sine phi to sine 2 phi, my Shapiro steps are all going to be halved. And so what happens is that when you're in this right regime, such that you have a 0 pi junction from this material, in addition to steps at the primary values that you expect for Shapiro, you start to see these half steps begin to form. And when we do these measurements on our nanowires, we do in fact see very predominant half steps. And in some cases, the half steps are even more prominent than the fundamental steps. And this is not what you would expect if you just had a skewed current phase relationship. You know the amplitude of each Fourier term should go down as you go to higher and higher harmonics. So you would never expect the half steps to be higher than the predominant steps. So there's some dramatic modification of the current phase relationship, which we are picking out both in our diffraction pattern measurements and in our Shapiro step measurements that we need to understand. For this particular material, so we've gone through a few variations on what it could be, working with Liang Fu with some topological phase transitions such that there's an intrinsic phase difference between the different bands of the topological superconductor and tin telluride. But what the inkling I have for what's actually going on, tin telluride, you may know, undergoes a ferroelectric distortion that becomes more prominent as you thin down the materials. Since crystalline symmetry and its mirror symmetry is so important to the surface state, different domains of these different ferroelectric distortions are bound to do something to the band structure. So I'm very interested, what does that do to the Andreev bound states? And how do I deal with the interface between these two different ferroelectric domains? And I think once we have a good understanding of how that works, we'll be able to explain both the magnetic diffraction pattern and these half steps.
So to be clear, you see this effect only in the nanowires and not in the films.
Yeah, but I think the nanowires, I don't think there's anything nano about them in the sense that there's no modification of the band structure, because the thickness of the wires is much, much greater than the Fermi wavelength. These things are doped pretty heavily. We're talking like 10 to the 19, 10 to the 20. And so for a few hundred by few hundred nanometer wire, that's basically a bulk.
So what's the difference?
So I think the difference just has to do to what doping with lead does to this ferroelectric transition. So to summarize, I started this talk by saying the key thing that I want at least you youngins to take home with us. We often talked about synthesis and growth of quantum materials, but one thing that, and those are extremely important things to continue to progress and get right and improve materials quality. But one key thing that we need to focus on is the characterization materials, and to formulate binary tests for saying certain things about, is there Majorana or is there not? Is this topological or not? And what, these exotic things associated with quantum materials, we need characterization tests that tell us something about those exotic properties in addition to what we know about the crystal properties. And so to illustrate that, I talked a little bit about Josephson junctions, which goes part of the way to being able to tease out certain aspects of quantum materials. The example I used was being able to infer that there are some highly transmitting states on the surface of this topologically crystalline insulator, states that are not there when we go to the topologically non-trivial or topologically trivial material lead telluride. And so by continuing to refine our Josephson measurements in addition to augmenting the types of measurements we actually do in the lab, I think another few years down the line we'll have a lot more to say about the characterization aspect of quantum materials. Thank you.